transistors share many similar properties superficially. The way they operate is
Sir,
completely
now it is coming.
MOSFET
Sir,
stands for
properly.
metal oxide semiconductor field effect transistor. Right now, that may just seem like a bunch
Sir,
of random
start it
words
with
mashed
starting.
together. But once you understand how it works, this name will make perfect sense. MOSFETs still act like switches by varying the voltage on one terminal, the gate. It changes the resistance between the other two terminals, the source and drain. Let's discuss the makeup of your MOSFET using an NMOS in enhancement mode as an example. With an NMOS, you have a P-type substrate
Screen is still, sir.
and then create two heavily doped N-type regions.
Sorry?
No, now it's going on.
Sir, everything
Screen
is
was
okay.
These two regions are called
Everything is
the
okay,
source
sir.
and the drain region. With our knowledge of
So make others
semiconductors,
mute.
you can see that you're creating a PN junction between the substrate in these two regions.
This is the structure of the MOSFET. This is P-type substrate, or it is called the body also. These are the two heavily doped regions. This is called source, this is called drain. Remember in the last class I said that the MOSFET is symmetrical. So one can use this as drain, this as source, or this is drain as this is source. So source and drains are not rigidly defined or strictly defined. One terminal can be used as source, the other terminal can be used as drain. And the current flow, as you all know, happens between high potential to low potential. So in a MOSFET, the current flow takes place from drain to source. The current flow takes place from drain to source. So the terminal which will be having higher potential will be acting as drain, and the other terminal which is at lower potential will be acting as source. So if this is, for example, is 5 volt and this is 0 volt, so this will be acting as drain. On the contrary, if this is 5 volt and this is 0 volt, then this will be acting as drain. And the current flow will be from drain to source. Whatever I have said, this is true for NMOS. This is the NMOS structure. This is N plus diffusion. This is N plus diffusion. We call this as diffusion. And this is the P-type substrate. So this is the N-channel MOS, or in short NMOS. If the substrate is N-type, or just change the reverse the polarity, something like if you take it N-type substrate and these are P plus, the corresponding MOSFET will be P-channel MOSFET. As I mentioned, I'll be using the term MOSFET to represent enhancement mode MOSFET, which basically dominates the industry. Almost all the MOSFETs that we use, that goes into your memory stick, that goes into your laptop, that goes into your cell phone, they are enhancement mode MOSFETs, and de facto I call them as MOSFETs.
On top of the substrate, an oxide, which acts as an insulator, is deposited. Then on top of that, a layer of metal is deposited, which finalizes the gate structure. Now you can see where the metal oxide semiconductor in MOSFET comes from.
So this is, although we call it metal, the modern transistors do not use a metal here, and typically heavily doped silicon is used, as conductive plate. You can consider the structure similar to a capacitor. This is one plate, this is another plate, and this is the insulator. The insulator is silicon dioxide, SiO2. This is heavily doped silicon. Heavily doped because as you dope it heavily, it becomes highly conductive and behaves like a metal.
Sir,
Yes.
sir, what is the reason behind using a heavily doped silicon instead of a metal?
Because we want to create a structure which will be made up of all silicon. Now this structure, why it is so popular and why it has revolutionized the IT industry is because it is made of all silicon. This is silicon, this is silicon dioxide, this is also silicon. It is heavily doped because as you know that doping increases conductivity. So if you consider you need basically two plates or it is a conductive plate, so one can consider that silicon which is heavily doped will behave like a metal easily. And the entire structure will be all silicon. This is silicon dioxide, and this is again silicon. So it is just to make sure you need, consider it's like a capacitor. A capacitor requires two conductive plates. Here the top plate, when we started the MOS, the initial phases of MOS used metal as the top plate. This silicon dioxide will remain as silicon dioxide, which is a perfect dielectric. And this is, as usual, the silicon. So, primarily, you can consider that entire MOSFET will now be made out of silicon, which makes to fabricate millions of transistors very easily.
So, if we use silicon instead of metals, then fabrication becomes easy.
This is one reason. Another reason is there. There is a something little complex. That's in terms of if you use the similar materials in the other plate and this plate, there will be some kind of what is known as the work function difference, which I don't want to discuss.
Okay, sir.
So I can refer this to a junction of two materials. When you consider a junction of two dissimilar materials, a contact potential is always developed. If you take a junction of two dissimilar materials, a contact potential will always develop. Okay. So if you use a metal here, typically the contact potential adjustment is a little challenging. So much easier will be if we use same material here, silicon here and silicon there.
Okay, sir.
So see, if you are building something and if you need different materials, for example, if you are making a circuit, ideally we should use minimum variety of components. What I mean is that my primary objective should be that if I am using a circuit, if I'm designing a circuit, I should try to use only one type of components. For example, transistors. The MOSFET, the use of MOSFET makes it easier to build most complex electronic circuits using transistors. Only, but typically we may also require resistors, we may require capacitors, and often we do not use, but rarely we use inductors. Even if you consider the resistors, if you are making a circuit employing resistors, you should try to minimize the variety of resistors. That means you should try to design the circuit using, say, for example, a resistor of value 1K. So everywhere you'll be using 1K. Does it make sense? If you think of designing a circuit where you need 1K, 2K, 3K, 4K, 5K, it's not a good design. Okay, so in case of the integrated circuits, MOSFETs are used in integrated circuits, and without integrated circuits, your handheld devices like the mobile phone cannot sustain longer. Okay. So integrated circuits have several advantages, and one of them is it consumes low power, very low power, and that's why you can carry your phone for a day, even more, without charging the battery.
From. But it may seem strange to have your gate being completely electrically isolated from the rest of the circuit. This is where the FET term comes in.
So you can see that this region, this is source and this is drain. In between there is P-type material. Okay. So you have something like a two PN junction. This is P, this is N, this is N, this is P. So two PN junctions connected in back to back. So there is no electrical connectivity between this region and this region. Electrical connectivity means some carriers, some charge carriers should be there, and whenever you are connecting two N plus materials, charge carriers should preferably be electrons. So as it's a P-type materials, no electrons are end up rare there. So the connectivity between the source and the drain is virtually absent.
Even though there isn't a direct electrical connection, the voltage on the gate creates a field effect. As we know from our studies about diodes, at a PN junction, a depletion region is naturally created even when there are no electric fields. This is the natural state when the gate voltage is 0 and the MOSFET is operating in the cutoff region. This is an operating region, not a physical region, which can be confusing. If you increase the gate voltage, that positive voltage will repel holes in the substrate away from the area between.
So there are several regions of operation of any device. For example, in a BJT, there are three distinct regions. One is cutoff. Cutoff means the current will be 0, and the resistance between collector and emitter will be very high, and it behaves like an open circuit between collector and emitter. Then there is active region. In active region of BJT, the collector current is proportional to base current. IC equals to beta IB. Please note here that IC equals to beta IB is true only and only in active region. I repeat, IC equals to beta IB is true only and only in active region. By active region, I hope you are aware that the base emitter junction is forward bias and the collector base junction is reverse biased. So in active region, the transistor is biased to work as an amplifier. And the third region is the saturation region, where both the junctions, emitter base and collector base, will be forward biased, and the collector, the resistance between collector and emitter will act like a short. That means it will be behaving like a closed switch. A transistor must behave well in this cutoff and saturation regions to be used as digital in digital circuits as switch, on switch and off switch. And if you want to use the transistor as an amplifier, you have to operate the amplifier in active region where IC is proportional to IB. Here we have, this is the source, this is the drain. When the gate voltage is 0, there is no connection, as been explained. And what we do when we apply a positive voltage, the positive voltage repels the holes from the P substrate, or this is the body.
Between the source and drain, an area called the channel region, this time a physical region.
The channel region means the separation between the edges of source and drain. And this is a very important parameter that's called channel length, L.
As the free holes leave the channel, only negative fixed ions are left, creating a depletion region across the entire channel. Besides this depletion region, an inversion layer of electrons starts to form at the source.
Two things are happening. When you apply a positive voltage, first you can consider the positive voltage will repel the holes. This is a p-type material. So in a p-type material, holes are there. So you are trying to, you are driving the holes out of this interface, this region. Okay. Now, if you apply a sufficiently high potential at the gate, of course, with respect to source and the body, then what will happen? Some electrons, whatever the electrons are available in the P-type body, will be attracted towards the upper layer of the channel. Okay, so two things happening. First, when you apply a voltage, initially the holes will be driven away from this upper layer of the channel. And then if you apply more potential, then electrons, whatever is there inside the P-type body, will be attracted and inversion layer will be created. Inversion layer means the upper layer will be filled with electrons.
And as the voltage increases, that inversion layer expands toward the drain. However, at this point, when the gate threshold is not yet equal to the threshold voltage, free carriers do not yet connect all the way from the source to the drain. This area of operation is called the saturation or pinch-off region. However, as the gate voltage continues to increase, increasing the electric field, and finally passes the threshold voltage.
So when you apply a gate voltage defined as the threshold voltage, then the channel will be created in the P-type substrate. So it's a P-type material, and by applying some potential that's called field, you have created a layer of electrons connecting between source and body, source and the drain. Okay, so this is the layer of electron that is created. And the threshold voltage is very important. This is the minimum voltage we requires to create the inversion layer. Why it is called inversion? Because the semiconductor is p-type, containing largely holes as the current carriers. So inversion means it is basically in this material we have created a region which is just opposite to that of its majority carriers. Okay, and mathematically speaking, the threshold voltage is the voltage necessary to be applied at the gate so that the concentration of electron in the inversion layer is equal to the concentration of holes in the p-type body. So if you consider the p-type body has a hole concentration of something like 10 to the power 16 per centimeter cube, the inversion layer will be, the threshold voltage defines the voltage necessary to create an inversion layer which will create a region containing the concentration of electron is equal to the power 16 centimeter cube per centimeter cube.
Electrons from the source and drain flow in and form an inversion layer of electrons that connects the source and drain regions. Now that they're connected, if a voltage is applied across the source and drain, a current will flow. The MOSFET is now operating in the linear or triode region. This is how, using a metal oxide semiconductor structure, you can use the field effect of a gate voltage to create a semiconductor switch. And to get a PMOS device, you have an N-type substrate and heavily p-doped wells for your source and drain. And the current carriers are holes instead of electrons. Also, I mentioned earlier that this is an example of an enhancement mode device. It's called an enhancement mode device because an increased gate voltage enhances the conductivity of the channel. Some MOSFETs are...
So, it is called enhancement mode because by applying higher and higher gate potential, you are able to create more and more carriers in the channel and thereby increase the conductivity between source and the drain. So higher gate voltage enhances the conductivity. That's why it is termed as enhancement mode MOSFET.
Increased gate voltage enhances the conductivity of the channel. Some MOSFETs are designed so that they naturally have a conductive channel, and a negative gate voltage is needed to actively turn it off. And these are called depletion mode devices. Conceptually, that's basically all you need to know to understand the mechanics behind MOSFETs. For the most part, everything stems from these operating principles. But there are a few things that I'd be remiss to not mention that can affect their operation. First is the channel length, L, the distance between the source and drain. Second is the channel width, W, which is how long the source and drain are. These two features are very important when it comes to designing a MOSFET. Third, in this example, we assume that the substrate or base was connected to ground. That's usually the case, but not always. No matter what, you need to make sure that the source and drain are at equal or higher voltage potentials than the substrate, or else you will forward bias that PN junction and get an unwanted current. This topic can be surprisingly confusing, and I personally believe that it's in large part due to the amount of terms, especially those that stand for the same thing, such as linear, triode, and ohmic, to describe the same region. Unfortunately, that's just the reality of the situation, and it will just get easier with experience and familiarity. I hope that this at least gives you a good foundation as you start to use or design MOSFET transistors, so you have an intuitive understanding of how these operate. If you like this video or you found it interesting, please subscribe to our channel and go to circuitbread.com and we'll...
Okay, so you have any other question?
Sir, please tell me what is a P channel? P channel and N channel.
Sounded interesting.
Let me close this. It is similar to the NPN and PNP transistor. Okay.
If the substrate is N type, then the channel is P type. Then the
Yes.
P channel.
Yes.
Okay, sir. Thank you, sir.
So if you alter P with N, then a P channel MOSFET is formed. That means wherever N is there, you have to use P, and wherever P is there, you have to use N.
Sir, it means for P channel, the gate potential must be negative.
For P channel, gate potential must be negative. Okay? Because you have to attract holes there to create the inversion layer.
Okay, sir.
Sir, can you please explain the depletion field effect transistor that works in depletion regions rather than enhancement mode, depletion mode?
Yeah. I will. One second. So my slides are visible.
Yes, sir. Yes, sir.
Yes, sir.
So let's see the structure once again. Okay. This is the channel region where things are happening. Okay. The conductivity of the channel is controlled by applying a field or voltage here. Field is directly connected to voltage. Whenever you apply voltage, a field is created. So traditionally, when we explain the structure, we consider this is the N-channel MOS. So N-channel MOS will have a body of P-type material. This is N plus, this is N plus. Okay.
Yes, sir.
And if this is P plus and this is P plus, and the body is
N channel.
N-type, then it becomes the P-channel MOS. Okay. This is the length of the channel, which is shrinking year after year, and as you shrink the length of the channel, the separation between source and the drain, it becomes a better switch, faster switch. Okay. Now let us talk about the depletion mode MOSFET. Depletion mode MOSFET, I don't want people should focus much on depletion mode MOSFET because it's not much of use in the circuit. But conceptually, there will be N-type doping beneath the oxide layer. So you have metal, this is the oxide, and then this is the P-type material. So at the top of the channel, a channel exists in case of a depletion mode MOSFET. So what I want to mean is that in between N plus and N plus, if you go to the upper layer, there will be a thin region which is doped with N-type material. So that means it will be N plus, then there is a thin layer of N, and then there is N plus. It simply means even if you do not apply any potential, there will be a channel in between source and drain. So at no voltage, a channel exists between source and drain. All right. So in enhancement mode, there is no channel at zero gate potential, and you apply potential at the gate to create the channel. In case of depletion mode, the channel is there inbuilt, and what you will do is that you will apply the potential to depopulate the channel. All right. So something like if you apply a negative potential, this N region will be depopulated, or depletion region will happen. And therefore the conductivity, as you apply more potential here, will decrease. And that's why called depletion mode. I'll try to explain it with better diagram as we go on. One thing has to be noted is that this is basically a 4-terminal device. The body is the 4th terminal. For N-channel MOS, it is connected to ground. For P-channel MOS, it is connected to the highest potential. For example, it is either VDD or it is typically connected to VDD. Maybe 5 volts, maybe 1.8 volts, whatever the maximum potential that you are using in your circuit. The requirement comes from the fact that you have to ensure that this PN junction, this is N plus, this is P region, this has to be the source body or the drain body junction has to be kept under reverse bias under all conditions. This is an essential condition. You have to ensure that the source body, this is the body, we call body or substrate. We will be using the term substrate for integrated circuits. Body, they are used interchangeably. So source body and the drain body, these PN junctions have to be kept under reverse bias in all circuit conditions. So to make this PN junction reverse bias, you have to apply some zero potential here, and this has to be this is the high potential, and this is the this is the PN junction. So P side should be connected to lower potential, and N side should be connected to higher potential. So any question about the structure?
And the body is at zero potential or ground potential, the body? Okay,
You have to make sure that this PN junction and this PN junction is always under reverse bias.
okay, sir. Thank you, sir.
Okay. So that you will be basically the entire region will be isolated by depletion region. So this is the typically one most important parameter of the Mosfet, that's called the channel length. And please note the structure carefully. This this region, the oxide layer, okay, it must cover the edges of the source as well as drain. What I mean is that the
హలో 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 మేడం నేను మీ దగ్గర కొరియర్ చేశాను ఆ కొరియర్ పోయిందో లేదో ఎలా అండి తెలిసేది వెస్ట్ బెంగాల్ अरे भाई माइक बंद कर ले यार अरे भाई म्यूट कर ले म्यूट कर ले भाई ऑफिस రావాలా
भाई म्यूट कर म्यूट చేసి
ఈ నంబర్ బాలరాజు బాలరాజు
Banavatu, please mute your mic. Mute, mute.
Banavatu Balaraju, his name is.
म्यूट कर लिया
Banavatu, please mute.
Okay, sir. He has done. He has done. So let's continue.
yeah. So what I want to point out is that the gate should not terminate at the edge of the source of the drain. It must extend little beyond the drainage, something like up to this point. Okay. So whenever you are drawing the structure of the Mosfet, please ensure that your gate covers the edges of the source and drain. Okay. So this is a very important parameter.
Here, what is in place?
Cover the edges of the source.
What is the terminology of in place?
One by one, please.
Sir, what is the need for the gate to cover the edges of the source and drain?
If you do not cover it up to the source and drain, it might happen. Let us consider the gate is up to here. Okay. Then what will happen? The channel will form only in this region, and there will be no channel here. Does it make sense? When you are applying potential here, the electrons will be attracted in this region, and there will be no inversion layer, or no layer of electrons to continue the channel up to the drain will form, will exist. So you have to ensure that the channel is formed between the source and the drain. It is necessary that it is the gate covers the edges of the source as well as the drain. And another important point to be noted is that the MOSFETs are mostly used in integrated circuits. And integrated circuits, the number of transistors we typically pack is several millions, in some billions also. It is very difficult to imagine what is a billion. It's just enormous number of transistors are packed into your mobile phone. Now, when you are packing, when you are creating 1 billion transistor, and you have to ensure that all the transistors will cover the gate will cover the source and the drain. Okay, it is possible that in some of the transistors, if you do not kind of do some kind of over design, some of the transistors may happen that the channel, the gate has come to this point, okay, and this point, and therefore the transistor will not work. And once the transistor doesn't work, the entire chip has to be thrown away. So to kind of guarantee that it will be covering the channel from the edges of the source and the drain, it is typically extended little beyond from this point to this point, so that even if there is a misalignment, even if the gate is slightly shifted right or gate is slightly shifted left, it's an automatic process. Then also the transistor formation will be guaranteed. Okay. Okay. So,
sir, what does that N plus mean, sir? Once explain the terminology of N plus.
N plus.
N-type drain and source.
This is the source and this is drain. N plus means we typically define 3 types of doping. One is N or P. That means it is moderately doped. When we write P minus or N minus, we want to mean that it is lightly doped. Doping is of the order of 10 to the power 15, 10 to the power 16. And if it is N plus, it is heavily doped. Something like 10 to the power 20 or so. So it denotes the extent of doping. If it is heavily doped, we represent it as N plus, heavily doped. N minus means lightly doped, and N means moderately doped. So the length is, you can see, is something of the order of 30 nanometer to 1000 nanometer. And the transistor that has gone into your cell phone will be of the order of even less, maybe 10 to 20 nanometer. And the research is going on to reduce the dimension of the transistor, say from 20 nanometer to 15 nanometer to 10 nanometer to 5 nanometer and so on, so that we can pack more and more transistors into an IC, and thereby we can add more and more functionality in one chip. More functionality means more operations, or more operations per unit time. So typically, this is a very important dimension. Then the width is something 0.1 micrometer to, it can vary depending upon the current requirement. When you need more current, the current is typically proportional to W. So IB is proportional to W, and it is inversely proportional to L. The current between drain and source, gate current is 0. Why gate current is 0? Gate current is 0, it is because it's basically an insulator that the gate is heating. So this is silicon dioxide. So the current cannot flow through a dielectric. low frequency current especially. So ID is the gate current is 0, and that's why its input impedance is very, very high, of the order of 10 to the power 10 to 10 to the power 12 ohm. So one can consider virtually it is infinite resistance.
স্যার
Yes.
স্যার আমাদের 11টা থেকে ক্লাস আছে আর একটা।
Okay, I'll stop here. So I would request everybody to watch that small video. I have posted the link once again, and if you have any questions about the structure or the terminology, we will take up in the next class. Any other question?
No, sir.
Sir, why the body is at zero potential?
Body is to be not at zero potential. Typically, it is at zero potential for NMOS. Remember, all the discussions that I have been talking is with reference to the N-channel MOS or NMOS. Okay. So here the body, the condition is that this is the body and this is the source. So this is N plus, this is P. So this is a PN junction. We have to ensure that this PN junction and this PN junction is under reverse bias.
Yes, sir.
So if you want to reverse bias this, so that there is no current between the source and the body and the drain and the body. If you want to reverse bias this, you will see that the body has to be connected to either zero or some negative potential.
Sir.
Yes.
Can you please send this PDF?
I will be sending this PDF once the classes are over.
Okay, sir.
Okay, sir.
Okay, thank you.
Thank you, sir.
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 Thank you, sir. Thank you, sir.